So far, we have been talking about atoms, individual atoms. But in many cases, atoms combine with other atoms to form molecules. And so molecules are the chemical combination of two or more atoms. And if these are two or more different atoms, then we have compounds. But most matter exists as these molecules or compounds instead of individual atoms. In fact, only the noble gas elements, or the noble gases, group 8 or 8A or 18 of the periodic table, are normally found in nature as isolated atoms. Instead, most matter is composed of molecules or compounds. Atoms may combine in order to become more stable. So all atoms ever want in life is to become stable, and by combining with other atoms, this helps to and to form molecules or compounds. This helps them to become more stable, and they combine with other atoms chemically through what we call chemical bonds. So a chemical bond is the attractive force that holds atoms together in a more complex unit. And so here we have, so all of these represent molecules, but not all of these represent compounds. So I want you to stop and make sure you could recognize the difference between molecules and compounds. So all of these are molecules, but which ones are compounds? So only the ones that have two or more different elements are compounds. So all are molecules. So these are molecules, but these are molecules of elements. The rest are molecules of compounds because they contain two or more different elements, so represented by the different colors. So white is used to represent hydrogen here, and red is used to represent oxygen. So that's water, which is both a molecule and a compound. But there are two broad categories of compounds that we will discuss. And so, but before we do that, let's get a refresher on what we mean by a compound. So a compound, we said, is a pure substance that contains two or more different elements chemically bonded together. Compounds are divided into two broad classes. So we have two main types of compounds. So we have ionic compounds and we have covalent or molecular compounds. And by the end of this chapter, hopefully you should be able to distinguish which of these are ionic compounds and which of these listed here in this table are covalent or molecular compounds. So going back to our chart about matter, so we said that all matter can be classified as either being a pure substance or a mixture. And then of the pure substances, we said we had two types, or flavors, elements, and compounds. And now we want to look in this chapter at the types of compounds. So the two types of compounds, so molecular or covalent and ionic compounds. So we kind of touched on this a little bit. So we said that atoms combine with other atoms in order to become more stable. But why do atoms form bonds? So bonding is a favorable process because it always forms a compound or molecule that is more stable than the atoms from which it is made. So the compound is more stable than the individual atoms from which the compound is made. And in bonding, elements will lose, gain, or share their electrons to attain the electronic configuration or arrangement of the noble gas closest to them on the periodic table. So we said that the noble gases, so like neon, are stable, so they don't form compounds, and so this has to do with the way their electrons are arranged. So stable because of how their electrons are arranged, which we call electron or electronic configuration arranged. And so the other atoms will try to lose, gain, or share their electrons so that they get an electronic configuration similar to those of noble gases. And in order to understand this process of bond formation, we have to understand a little bit about how electrons are arranged within the atoms. And so electrons occupy these specific energy levels, so that are specific distances from the nucleus. And the energy level, so which we also call a shell, so kind of like an onion has layers, so we could think of it like that. But the outermost layer is called the valence shell. The outermost energy level, so the one that's furthest from the nucleus, is called the valence shell. So the chemical properties of an element depend on the number of electrons in the valence shell. The group number, using the US system, so 1 through 8, tells us how many electrons are in the valence shell. So remember I said that one numbering system has advantages sometimes, and the international or the US numbering system has an advantage sometimes, or in some cases, and the international one has advantages in other cases. Well, it turns out that when we're thinking about how many valence electrons an atom has or an element has, then the group number, according to the US system, is easier to think about. So the group number using the US system tells us how many electrons are in the valence shell. The electrons in the valence shell are called valence electrons. And so elements in the same group have similar electron arrangements or configurations. And so we said that the number of electrons in the valence shell determine or influence their chemical properties. So if all elements in the same group have the same number of valence electrons, then this helps us to understand why all elements in a group will react or behave similarly in terms of their chemical properties. So elements in the same group have similar electron arrangements or configurations. So elements in the same group have the same number of valence electrons. And the group number, 1A through 8A, equals the number of valence electrons for the main group elements. So that is not the transition metals. The only exception is helium, which is in group 8, but only has 2 valence electrons. So helium has 2 valence electrons, even though it's in group 8. And the chemical properties of a group are therefore very similar because we have the same number, or they all have the same number of valence electrons. So in group 1, those elements have 1 valence electron, and even though hydrogen isn't a part of group 1, the reason why hydrogen is placed here because it has 1 valence electron. So we have group 1 with 1 valence electron, group 2, group 3, group 4, group 5, group 6, group 7, group 8. And so now we see that group 8 has 8 valence electrons, and so these are the noble or inert gases. And this is the explanation as to why they are stable. It turns out that 8 valence electrons is desired. So, and we'll talk more about that later on. But because they have 8 valence electrons, this makes them stable. So how are compounds formed? So a chemical bond is the attractive force that holds atoms together in a more complex unit. There are 2 main types of chemical bonds. So ionic bonds and covalent bonds. So ionic bonds result from the transfer of electrons from one element to another. So that is, we have one atom that loses an electron and another atom that gains through that transfer of electrons. So when we have an attractive force that results from the transfer of electrons, then that's an ionic bond. And then covalent bonds result from the sharing of electrons between 2 atoms. So instead of the transfer, they share these valence electrons. So again, ionic bonds are formed through the transfer of electrons from one atom to another, and in covalent bonds we have the sharing of electrons. Although this is the first time in all these years of me using this slide, I've noticed that this chlorine doesn't have the correct number of valence electrons. So chlorine is in group 7, and it should have 7 valence electrons. So, but here is shown as only 1, 2, 3, 4, 5. So there should be 2 more shown. Okay, yeah, I never paid attention to that. But that story will come later. But the take-home message from this slide is that there's the transfer of electrons that result in an ionic bond, and in a covalent bond we have the sharing of electrons. So our first type of compounds that we will discuss, ionic compounds. So ionic compounds consist of electrically charged ions that have a strong electrostatic attraction for one another. So previously we've been talking about a neutral atom where we have equal number of protons. Protons is equal to number of electrons. Now, we just said that an ionic compound results when one atom loses an electron and the other gains an electron. And so if we look at the original atom, if it loses an electron, then we no longer have this balance of charge in the atom, so we have more positive charge. And likewise, in the other atom, if it gains an electron, then we no longer have this balance of charge. We have more electrons than protons, and so then we form this negatively charged atom, which we call an ion. So charged particles are called ions. So positively charged atoms with more protons than electrons or negatively charged atoms that have more electrons than protons are called ions. And so an ion is formed when we have these unequal charges between positive and negative protons and electrons. So what is an ion? An ion is an atom or a group of atoms that is electrically charged as a result of the loss or gain of electrons. So due to an unequal number of protons and electrons. And we have a special name for a positively charged ion. We call it a cation, and we have a special name for a negatively charged ion. We call it an anion. So, more about ions. Metal atoms typically tend to lose electrons. So metal atoms. So where are those found on the periodic table? So on the left. So we talked about their position on the periodic table. So metal atoms typically tend to lose electrons. When this happens, the atom has less electrons than protons. And so that is, we have more protons than electrons. And so there is a net positive charge. That is, a positively charged ion called a cation is formed. A cation has fewer electrons than protons. So if we start with a neutral sodium atom, sodium is a metal found in group 1 of the periodic table, and we start off with 11 protons, 11 electrons. So we have an electrically neutral atom. And so sodium loses an electron, and now we have an imbalance of protons and electrons, or positive and negative charge. So we have 11 protons and 10 electrons, so we have a net positive charge. And so we indicate that the charge, the overall charge, in this case, if it's just 1, the 1 is assumed, so we write the charge as plus, but really that means plus 1, and we kind of do it like that, 1 plus. And if it was in group 2, it would be 2 plus, but Na plus, so a positively charged ion called a cation. Now notice here that we did not change the number of protons, because if we did, then we would have a different element, because it is the number of protons that determines the identity of the element. So when we form these bonds, we're not changing the number of protons, we're just changing the number of electrons. Non-metal atoms, on the other hand, which are found on the right of the periodic table, typically tend to gain electrons. When this happens, the atom has more electrons than protons, and there is a net negative charge. That is, a negatively charged ion called an anion is formed. An anion has more electrons than protons. And so if we look at chlorine, so we have 17 protons, 17 electrons, and chlorine gains an electron. Then we now have 18 electrons, and we have 17 protons, so we have a net negative charge, and so we have a chloride, or Cl minus ion. So there's one more negative charge, so we have a net charge of -1. So we indicate that with this superscript of a negative. And if it's just one, if no number is shown, that's assumed to be 1. So -1. So again, why do atoms form bonds? So the octet rule states that atoms tend to want to have 8 electrons in their valence or outermost shell. That is 8 valence electrons. In general, atoms are most stable or least reactive when their valence shell has 8 valence electrons. Only the noble gases have 8 valence electrons. This explains why the noble gases are inert. That is, they undergo few, if any, chemical reactions because the noble gases are stable. Why are they stable? They have 8 valence electrons. In forming an ion, an atom of a main group element loses or gains electrons to obtain the electron configuration of the noble gas closest to it on the periodic table. That is, they're trying, in most cases, trying to get 8 valence electrons. To achieve an electronic configuration of a noble gas, metal atoms tend to lose electrons from their valence shell. That is, they want to have the same electronic configuration as the noble gas closest to them on the periodic table. So let's look at sodium as our example. So sodium is in group 1 and has 1 valence electron. So sodium has 1 valence electron, and the noble gas closest to sodium is neon, so the one right before it on the periodic table. And so neon is stable, and so what is the electron configuration of neon? So in terms of its valence shell, so neon has 8 valence electrons. And so Mr. Sodium says, hey, if I were to get rid of this lone valence electron, then my electron configuration would look identical to Mr. Neon's. And so I want to be stable like neon. And so sodium loses this valence electron, and now his valence or his electron configuration looks identical to that of neon. But notice that since the number of protons hasn't changed, it's still sodium. So neon has 10 protons, sodium has 11. And since there is now this imbalance of protons and electrons, we have more. So since it's lost an electron, we have an imbalance. We have more protons than electrons, so more positive charge. So we have a net charge of +1. So we have a sodium cation, but the electron configuration of the sodium cation is like that of a neutral neon atom. So that was just an example of cation formation. Now let's look at an example of anion formation. So to achieve an electronic configuration of a noble gas, non-metal atoms tend to gain electrons. So they too want to have the same electronic configuration as the noble gas closest to them on the periodic table. So let's look at chlorine as an example. So chlorine is in group 7. So chlorine has 7 valence electrons, 1, 2, 3, 4, 5, 6, 7. And so chlorine looks over to his or her closest noble gas neighbor, argon. So argon is right next door to the right. And chlorine says, hey, Mr. Argon, you're pretty stable. If I could just gain one more valence electron, then I would have an identical valence electron or electron configuration as you do. And so chlorine gains an additional valence electron and now looks identical in terms of how the electrons are arranged to the argon atom. Now, since chlorine gained an electron, we have more negative charge than positive charge, and we have one more negative than we do positive, so we have a net charge of -1. So we formed a chloride or negative chlorine anion, and it looks like argon in terms of its electron configuration. Okay, so in these problems we will look at how we write the symbols for ions. So write the ion formed when a barium atom loses 2 electrons. And then the ion formed when a phosphorus atom gains 3 electrons. So what we could do is look at the periodic table, and I have one on the next slide. If you look at the periodic table, and let's go with barium. So here is barium. And so how do we know how many protons barium has? So we look at the atomic number. That tells us the number of protons. And in a neutral atom, we know that we start with 56 protons and 56 electrons. So we have the same number of protons and electrons. And then, so if we lose 2 electrons, then we now have 56 protons and we have 54 electrons. So that is, we have a net charge of +2. So we have 2 more protons than we do electrons, and so we say Ba2+. Now really, you didn't have to look at the periodic table because you didn't really need to know the exact number of protons and electrons, as long as you know that there are 2 fewer negative charge than positive charge, so that would mean that there's a net charge of +2. Likewise, if in this example, so the ion formed when a phosphorus atom gains 3 electrons, so we know that we'll have a net charge of -3. So we don't really need to know exactly how many protons and how many electrons there are in phosphorus to solve this problem, but if that makes you feel a little bit more comfortable, you could go through it how we did in the previous problem. But you should come to the conclusion, so there's an excess of -3 charge, or net 3 negative charge, because there's 3 more electrons than protons. Then for this one, write the ion symbol for an atom with 9 protons and 10 electrons. Identify it as a cation or anion. So let's do that part. So which element are we talking about? How do we know? So we said that the identity of an element was given by the number of protons. So we know that this is an element with 9 protons. So looking at the periodic table, fluorine is the element that has 9 protons according to the atomic number. So we have fluorine, and so there's 9 protons, 10 electrons, so there's going to be a net charge of -1. So F minus, so -1. So this is an anion because it's negatively charged, so F minus. And then write the symbol for the ion shown. So we have 3 protons. So again, make sure you're pausing the video and coming to the answer on your own. And then coming back to make sure that you were on the right track. So 3 protons, so that is lithium. So Li. And so now to write the symbol for the ion, we need to know the number of electrons in comparison to protons. So we have 3 protons, 2 electrons. So 3 protons, 2 electrons. So we have a net positive 1 charge. So the symbol would be Li plus. So there are some trends that we can use rather than having to think of how many protons versus how many electrons when writing the ion symbol. So it turns out that there are some patterns that we observe as it relates to the ion that is formed by a particular group of elements on the periodic table. So group 1 will always form a cation with a particular charge, and likewise group 2. So elements in the same group form ions of similar charge. For metals in groups 1, 2, and 3, so we said the metals form cations, so the group number is equal to the charge on the cation. And then for nonmetals in group 6 and 7, the charge is equal to 8 minus the group number. So the anion charge is equal to 8 minus the group number. So we say 8 minus group 6, so we know that it's going to be a charge of 2, but we have to remember that that's negative. So another way that you could have done that was say 6 minus 8, which gives you negative 2. So elements in group 6 form anions with negative 2 charge. And so going back to our previous examples, so fluorine is in group 7. So these ones form anions with negative 1 charge, and these ones form anions with negative 2 charge. Now, why is there no trend for group 8 or group 18? So remember, these are stable, so these typically don't form ions. So we don't look at the patterns for those ones. But then these are +1, +2, +3, and then -1, -2, and then -3. Okay, so again, group 1, they form cations of +1, group 2, +3. Group 2, cations of +2, group 3, cations of +3. And then group 6, -2, group 7, -1. And so then I would encourage you, when you are solving these types of problems, to write the charge above each group that charge corresponds to on your periodic table. So just to make it a little bit easier. So what kind of helps me is the value is the same. So +1, -1. So on the outside, +1, -1, then -2. +2, then -2, and then this one is +3 and -3. So +1, -1, +2, -2, +3, -3. So those are the patterns. So lithium, actually, what ion does it form? It's in group 1, so Li plus. Beryllium, which ion does it form? Be2 plus.